Okay, for 3.35, you are given a wave function and you are asked to find the momentum space equivalent, then to find the magnitude squared of both the position and momentum space equivalents, sketch the resulting graphs, determine their corresponding widths, and then note what happens to each side, or what happens to each width as n goes to infinity. Finally, using these estimated widths, to find estimate as proxies of delta x and delta p, check that the uncertainty principle is satisfied, and then also explain why you can't try using sigma p in order to try and find the uncertainty through an expectation value integral. So let's take this one by one. Step one is going to be to find magnitude psi squared. And this is pretty easy, right? This is going to be equal to 1 over 2n lambda, and then the complex exponential cancels itself out from negative n lambda to positive n lambda, and then it's going to equal 0 otherwise. Okay. Now let's do the momentum space wave function. So phi of p comma 0 is going to be the Fourier transform of the position space wave function. So we're going to do 1 over the square root of 2 pi h bar times the integral from negative infinity to positive infinity of e to the negative ipx divided by h bar multiplied by the wave function psi of x comma 0, closing it off with a dx. In that case, plugging in psi of x comma 0, this is going to give us 1 over root 2 pi h bar integral from, and here, because our wave function is 0 outside of the range of negative n lambda to n lambda, this integral collapses from an infinite integral into just one from negative n lambda to positive n lambda, because for every other value, the wave function is going to equal 0, so they might as well not play a role in your actual infinite summation, right? So this is going to be e to the negative ipx divided by h bar multiplied by 1 over square root of 2n lambda multiplied by e to the positive I 2 pi x divided by lambda dx. Just make sure that my numbers are right. I 2 pi x over lambda. Yeah, that's correct. Okay, now let's move all the constants out. So this is going to give us 1 over 2 and then square root n pi h bar lambda by moving the constants here out to the other side of the integral, right? Now we have negative n lambda to positive n lambda of this two exponentials that are multiplying against each other, so we just add them, right? Or we add their internal exponents. So this is going to give us an exponential of negative ipx divided by h bar added with I 2 pi x over lambda. Now let's distribute out some common factors. So this is going to give us the same thing at the front, so I'm just going to copy and paste this. Now in exponential, so looking at both of these, they share an I and they share an x. So this is I times some ratio times x. So this is going to be I negative p over h bar plus 2 pi over lambda multiplied by x dx like this. Now, for simplicity's sake, we're going to want to combine these two fractions so that we get one single ratio. So this is going to give us the same thing as before. And then the complex exponential of I, and then combining these two, this is going to give us negative p lambda plus 2 pi h bar over h bar lambda multiplied by x dx. Let me just make sure that my math is right. Yeah, and out of convention's sake, I'm going to switch the order of this around because I don't like having negatives at the front. So this is going to be 2 pi h bar minus lambda p. And now we can take this integral, right? This is just a single complex exponential, which is a relatively simple thing to take an integral for. This is going to equal 1 over 2 square root n pi h bar lambda multiplied by our complex exponential, but also the reverse of this fraction. So we're going to get h bar lambda over I times 2 pi h bar minus lambda p, and then multiplied by our complex exponential, I 2 pi h bar minus lambda p over h bar lambda, x evaluated from negative n lambda to positive n lambda like this. And now let's see, what can we cancel out here? So there's immediately the h bar lambda, and the root h bar lambda at the bottom gives us a root h bar lambda above, which cancels out this and this. Now you're left with 2I root n pi, and then this is all multiplied by 2 pi h bar minus lambda p. Let's clean this up a little bit. Let's rewrite this as a full fraction. So this is going to be 1 over 2I multiplied by the square root of lambda h bar over n pi, like that. And finally on this side we have our exponential. So this is going to be exp of, what is that? If I multiply this by n lambda, the lambdas cancel out, so this is going to be in 2 pi h bar minus lambda p over h bar, I think. In 2 pi h bar minus lambda p over h bar, yeah. And then this is subtracted by complex exponential, same consolation, but this time there's a negative in front, so negative in 2 pi h bar minus lambda p over h bar, like that. And from here, I am now working with two complex exponentials subtracting off of each other that both have the same internal factor. So instantly that tells me that maybe I should try using a Euler identity and converting this into a sinusoid. So I know that, for example, e to the ix is equal to cosine of x plus I sine of x. Now, there's multiple ways to sort of proceed at this point. Intuitively here, what I see is that there's a 2 pi, there's a 2 pi n, right, in both of these factors. And if we can split those off, because this is really an exponential of like two things together, right? Because this fraction can be split apart into two terms. I can maybe make this a little bit simpler by peeling off an e to the in 2 pi h bar somehow. And from that point, I can then plug that into this and get cosine 2 pi, sine of 2 pi, which cancels out to 1 and 0 respectively, which does, you know, basically allow me to ignore an entire part of this exponential. So let's try that. So exp of in 2 pi h bar minus lambda p over h bar. So since this is an exponential, immediately my first instinct is to try to resplit this back into two separate fractions, which then allows me to rewrite this as the product of two complex exponentials, right? And this looks like a pretty nice simplification. This is actually just equal to exp of in 2 pi minus in lambda p over h bar, like that, right? Similarly, exp of negative in of 2 pi h bar minus lambda p over h bar is going to equal exp of negative in 2 pi plus in lambda p over h bar, like that. And then if we split these up further, this is exp of in 2 pi times exp negative in lambda p over h bar. This is then exp negative in 2 pi exp positive in lambda p over h bar. And now I have exp of in 2 pi. N is always just going to be a positive integer, so this is exp of a multiple of 2 pi, right? Or I times 2 pi. So going back to this, right, e to the I times 2 pi n is going to equal cosine of 2 pi n plus I sine of 2 pi n. Cosine of 2 pi n, or any multiple of 2 pi n, is always going to give us 1, and sine of 2 pi n, or any multiple of 2 pi n, is always going to give us 0. Similarly, if I plug this in, on this side I have negative 2 pi n. Well, 2 pi n and negative 2 pi n are basically the same point on the radian circle, so because of that, both of these terms nicely cancel out to just 1. This is just 1, this is just 1. So what I'm left with now is phi of p comma 0 is equal to all the stuff I have at the front, and then multiplied by exp of negative in lambda p over h bar minus exp positive in lambda p over h bar. Is that correct? E to the negative INP and then e to the positive INP. Yes. Okay. And now I have, once again, two complex exponentials, but now I've made them a little bit simpler because I've gotten rid of the 2 pi term. What I have left is the same thing, and once again, because I'm dealing with two complex exponentials, this implies that maybe I want to simplify this down somehow and turn this into a sinusoid through Euler's identities. In this case, what we have instead is that, now that I'm done simplifying this, I don't want to try doing this again. Instead, maybe I want to turn this into a cosine or sine term. And since this is a minus expression, that tells me it's a sine. I can somehow convert this into a sine expression, because I know that also from Euler's identity, e to the I times x minus e to the negative I times x divided by 2i is equal to sine times x, right? So in that case, let's rearrange this and get the positive at the front. So if I then, if I add a negative at the front here, and pi divided by, or times 1 over 2 pi h bar minus lambda p. If I add a negative at the front, I can then switch the order of this around, and now I have exp I n lambda p over h bar minus exp negative I n lambda p over h bar like this. And at this point, well, this expression right here is just going to be equivalent to 2i sine of n lambda p over h bar, right? So in that case, let's plug this back in, and now we have our actual equation for phi, or our final simplified equation for phi. Phi of p comma 0 is therefore equal to negative 1 over 2i multiplied by square root lambda h bar over n pi multiplied by 2i sine n lambda p over h bar divided by 2 pi h bar minus lambda p. The 2i here cancels the 2i here, so that leaves us with a phi that is equivalent to negative square root lambda h bar over n pi multiplied by sine of n lambda p over h bar divided by 2 pi h bar minus lambda p. Okay, now if we want to take the magnitude squared, that's just a matter of taking this. There's no imaginary terms here, so we just take the squared, right? Magnitude phi squared is therefore equal to h lambda h bar over n pi times sine squared n lambda p divided by h bar over 2 pi h bar minus lambda p squared. Okay, so now I have my magnitude phi squared and I have my magnitude p squared. I am now going to want to graph this, right? Let's underline these two, right? So magnitude psi squared is pretty simple to graph. This is just a straight line, but magnitude phi squared is going to require us to massage the variables a little bit because we have a lot of constants here. If we try to plug this into Desmos, we're going to get a bunch of errors, right? So instead of trying to graph in terms of p, recognize that your sine squared term is in terms of n lambda p over h bar. And let's hypothetically define a new variable, gamma, which is equal to n lambda p divided by h bar. Or actually, no, let's leave out the n. This is going to be equal to lambda p over h bar, in which case phi of gamma comma 0 magnitude squared is therefore going to equal lambda h bar over n pi multiplied by sine squared of n times gamma divided by 2 pi h bar minus lambda p squared. Recognize that down here, right, this term you can pull out an h bar squared in order to get rid of this h bar and then add an h bar at the bottom. Like that, right? So at that point, in this case, the h bar squared cancels the h bar on top. So what you have left is now magnitude phi of gamma comma 0 squared is equal to 1 over n pi h bar times sine squared n gamma over 2 pi minus gamma squared, like that. And finally, recognize that h bar is a constant, right? So there's nothing necessarily stopping you from just absorbing it along with the pi and just saying that this is equal, finally, to just some arbitrary constant that you can determine, because ultimately this is just going to be a scaling factor to make sure that your graph is actually readable, and you can just set it to just whatever arbitrary value on Desmos gives you a readable graph. So this is going to be some constant c divided by n times sine squared n gamma divided by 2 pi minus gamma squared, like that. And that is the actual graphable function that you're going to be working with in Desmos. Okay, I just did a jump cut right now. Basically what I did is I just took these wave functions and I plugged them into Desmos. Psi, or the position space wave function, is just a constant, right? This is n is a number, lambda is the wavelength, which is hypothetically a constant number. So because of that, this is ultimately just going to give you a flat line. What's going to happen, though, is that as n gets larger for successive values, right, n equals 5, n equals 50, n equals 500, and so on and so on, this is going to get more and more spread out because your limits are going to get more spread out as you multiply them by larger and larger scalars. And also, this term is going to get closer to 0, so you're going to have something that is, you know, as it spreads out, is getting closer and closer to the 0 line, and is getting wider and wider. In contrast to that, phi, if you plug this in, assuming that you plugged in some value for c, which is, once again, an arbitrary value, assuming you plug in some scalar for c that allows you to actually view the graph, and it's not just like something that's super close to the 0, you're going to get a sinusoid that looks like this. So now, if this goes to infinity, right, what you should see as you sort of increase the slider for n up to 5, 10, 500, etc., is that this graph gets more and more peaked around this given central point. So at like n equals 500, for example, it looks a little bit like this, where, oops, there we go. It looks a little bit something like this, where, you know, the graph is, it's still above 0. I'm just bad at drawing this, but the graph gets very narrow, very heavily peaked around the middle point that we marked out in the green dashes, and everything else sort of just goes away, or everything else like starts tending towards 0. So all these fluctuations on this side get smaller and smaller and smaller. What this physically is implying is that as your particle, which is hypothetically right now in some sort of infinite square well, because you're sort of enforcing it with the piecewise condition that it equals 0 outside of a given area, right? Supposedly, what this is telling you is that as your energy levels get higher, the value, or the possible values for position, start getting more and more spread out, right? So position becomes more and more indeterminate, whereas in contrast to that, the momentum of the function gets more and more determinate, centered around some specific value. And this at a glance should be, you know, agreeable with the uncertainty principle, because the uncertainty principle tells us that between x and p, as you know one with more and more detail, as it becomes more determinate, the other value becomes more and more uncertain, aka it takes on a range of indeterminate values. So now let's actually try to find the width as per the instructions of this problem and use them as approximations of delta x and delta p, right? And in this case, what they're determining as wx and wp is basically the width of the wave function between one peak to another, right? So for the purpose of x, let me just make sure I'm in black. This is a pretty trivial thing, right? Or not p, with x. This is pretty trivial because really this is a flat line. The width is whatever this width is, which in this case it's going from negative n lambda to positive n lambda, which means that it's 2 lambda or 2n lambda, right? Now, in contrast, if we want to find the width of p, we can recognize that, hey, this is ultimately a sinusoid. Right? It is a sinusoid that is being modulated by some expression that comes from c over n times 1 over 2 pi minus gamma squared. So ultimately, this fundamentally takes on the form of something that looks like magnitude phi squared is proportional to this concept of like a sine bx plus c plus d, which is like, it's just a sinusoidal equation. I'm sorry, I'm sort of losing the ability to speak for a little bit for some reason. The d term here is just 0 because this is not adding onto anything, right? You have some a expression, which is the coefficient at the front, and then you have a bx term, which is n times gamma, and then your c term is also 0 because this is not, you know, it's not n gamma plus something, right? And for an expression like this, ultimately the wavelength of this sinusoid is defined as lambda is equal to 2 pi divided by the magnitude of b. So our question now is just to find out what is b. Well, that's a relatively simple thing as well, because we know that n gamma is equal to n lambda p over h bar, and if p is sort of the equivalent of the x here, right? And in fact, just to make that extra clear, let's rewrite this as p, because this is an equation where p is our main variable, not x, right? In that case, our b term is equal to n lambda over h bar, because this is b times p. Right? So that means that our wave function, or our wavelength lambda, which is equal to our approximation of with p, is equal to 2 pi divided by the magnitude of b, which is equal to 2 pi times h bar over n lambda, like this. So that means that omega, or w, or omega, whatever it's called, omega x times omega p is equal to 2n times lambda multiplied by 2 pi h bar over n lambda, in which case the n lambdas, that's not what it's supposed to be. N lambda wp equals 2 pi. Oh, yeah, it is. Okay. This cancels with this, so what you're left with is 4 pi h bar. And this does, in fact, agree with the uncertainty principle, because we know that the uncertainty principle states that delta x times delta p has to be greater than or equal to h bar over 2, and 4 pi h bar is indeed greater than h bar over 2. So therefore, our uncertainty principle is satisfied. Okay, for the final part of this question, it is asking us, why is it that if we try to use I think this is called sigma. Yeah, sigma p. Why does this give us an invalid result? So if we try to approach this problem from the perspective of expectation values and sigma and stuff like that, sigma p is defined as defined in chapter 1 is equal to the square root of the expectation value of p squared minus the expectation value of p squared, like that, right? So let's just take this for example, p squared. If we wanted to find the expectation value of p squared for this expression, this would be bracket of phi p squared phi, and since this is in p space, the p operator is just equal to p in p space, so this is actually equal to just the integral from negative infinity to infinity of magnitude phi squared multiplied by p squared times dp. So if we write that out, this is equal to integral from negative infinity to infinity of lambda h bar over n pi times sine squared n lambda p over h bar divided by 2 pi h bar minus lambda p squared dp. Let's just take the initiative and move this off to the other side, and then take this a little bit closer. And what you should immediately notice is that this integral diverges. This is actually equal to infinity. The reason why is because you have a p squared term on top and then a sine squared term, which, the sine squared term oscillates between 0 and 1, so this is an oscillating term, and you have a p squared term on top and sort of something that goes like p squared on the bottom. So ultimately this is proportional to something along the lines of an infinite integral of sine squared. And that's obviously going to diverge to infinity. So this apparently is not valid. And now we're being asked, okay, why is this not valid? And I think for this one, it really is like, if I just tell you, it's going to be like, oh, obviously, of course. So I'm going to try my best to sort of approach this from the perspective of sort of what you have to do to actually try and like get to the point of realizing why this doesn't actually work. So really, for any sort of fundamental system, or let me put it this way, whenever you're trying to figure out why an established formula is not working, assuming that you did everything right, more often than not, the reason is always going to come back to one of the fundamental requirements for you to use this formula being broken. And this might be something that you have forgotten because it was first brought up way back in chapter 1, but one of the things that we required as a condition to have a valid normalizable wave function that actually behaves as a realistic system is that the wave function and the magnitude squared of the wave function both need to be continuous. So because of that, you at the very start are given a discontinuous wave function. This is a piecewise wave function, because if you take this wave function and you take the magnitude squared, you get this, right? And there's discontinuity here and discontinuity here. So the magnitude squared of the wave function is discontinuous. Automatically, this system is not a realizable system. It is some sort of abstract system that we have created through mathematics and cannot actually exist in reality. So because of that, you really sort of like all of the techniques you've learned up until this point that you could use on this system, they all have sort of a possibility now of breaking down and not working properly. In this case, the thing that breaks down when you try to create a non-physically realizable system like this is the expectation values. If you try to find the expectation value of p squared in this system, what you'll find is that the resulting integral diverges. If this were an actual physically realizable system, then obviously it would not diverge and everything would work as intended. So really, I would say the thing to keep in mind, or the thing that is very important, I would say, to sort of always remember, is what are the fundamental rules that are required for you to actually interact with your given problem, or be this quantum mechanics or classical mechanics or any other physics field or any other science field, for example, for that matter. Really, the important thing is to remember that there are fundamental rules that everything else is sort of built upon, and you really have to remember those rules, because otherwise, if you suddenly decide to break one of those rules by arbitrarily creating a system like this, you're going to run into problems that you didn't expect to have. Outside of that, this is the completion of this problem, so that's it.